we fix the alpha ray, okay? The probability of committing a type 1 error. But because we've done multiple independent samples t-tests, what is the actual probability? The actual probability, okay, of committing a type 1 error, okay, across this whole experiment here, okay, this set of independent samples t-tests. Well, let's just try to rationalize what that would be, okay? So let me just move this page here, and let's start a probability calculation, okay? So let's say that we have, okay, so we have three groups. We have A is compared to B, we have A is compared to C, and we have B is compared to C, okay? And each one has an alpha, 0.05, 0.05, and 0.05, okay? These are the probabilities of committing a type 1 error in this case here. So let's ask a different question. When I do the 3 experiments, what's the probability of committing no error at all, okay? So what I'm interested in is across the three experiments, okay, what is the probability of committing, okay, no error, okay? So that's a different question. We know the probabilities of committing an error. What's the in the individual cases? What's the probability of committing no error? Because if we know the probability of committing no error, we can take it away from 1, which gives us the probability of committing some error. Because the ways that we could commit a type 1 error when we do 3 experiments is, well, we could commit it here and not here and not here. We could commit it here and not here and not here. We could commit it here and not here and not here. We could commit the first 2 experiments could commit an error and not the third. The first and the third could commit an error and not the second. The second and the third could commit an error and not the first, or all 3 could commit errors. So many ways that we could actually commit type 1 errors when we do 3 experiments, yeah, across the whole collection of experiments. So let's calculate this probability of committing no error, okay? So no error. So what's the probability that we commit no error, okay? Well, what does that mean, okay? Well, then that means, let's call this experiment 1, experiment 1, experiment 2, experiment 3. So if there was no error, well, then that means that there was no error committed in experiment 1. So that means that this probability here is the probability of no error is the same as the probability that there was that experiment 1 had no error, okay? So experiment 1 had no error, and experiment 2 had no error, okay? None, okay? And experiment 3 had no error, okay? If that makes sense, yeah? So if we didn't commit an error, it means we didn't commit an error here, and we didn't do one here, and we didn't commit an error here, okay? Which is the multiplication rule, okay? Now, these are all independent of each other, okay? These experiments, yeah? Okay? So the multiplication rule will tell us that this probability now, the probability of no error, is simply the product of these individual probabilities. So the probability that experiment 1 has none times the probability that experiment 2 had none times the probability that experiment 3 had none, okay? That would be the overall probability. Now, we know the probability of committing a type 1 error, so the probability of no error would be 1 minus that probability. So in this case, this gives us 1 minus our alpha, okay? In this case here, it'll be 1 minus our alpha. The alpha is the same across the experiments, and in this case here, it'd be 1 minus alpha. So when we have 3 groups, okay, when we have 3 possible pairings, yeah, the probability that there's no error across the experiment, the set of experiments, okay, is equal to 1 minus alpha, in this case raised to the power of 3, okay? So that means, therefore, the probability of committing an error, wherever it is, okay, somewhere, okay, must be equal to 1 minus alpha to the power of 3 in this scenario. And to be specific, when alpha is equal to 0.05, the probability of a type 1 error being committed, okay, is actually 1 minus 0.05 raised to the power of 3 in this situation when we've got 3 possible pairings, okay. What does that give us? That gives us 1 minus 0.95 raised to the power of 3, which gives us, if I'm not mistaken, this comes in around 14. I'll just grab my calculator, okay, or 14%. So let's have a look at this. So now we have 1 minus, can you see that okay? Maybe I'll move it over here. No, maybe I'll just move it here. Oh, the light is in the way. 1 minus 0.95 raised to the power of 3, okay, gives us a value of 0.14. So it's 0.1426. The two decimal places 0.14. So actually, the probability of committing a type 1 error across these all these experiments is actually proportional. It's proportionally equal to, you've got, it's 0.14, which is about 14%, okay. So that's an important observation now, yeah, and that's the reason why we don't do independent samples t-tests. So let's just keep in mind here now, in the 3-group scenario, the probability of committing a type 1 error when we do an ANOVA is fixed at alpha is equal to 0.05, okay. When we do separate t-tests, each one has a probability of committing a type 1 error, and actually finding or committing one of those errors across all experiments, okay, committing